Hendrik Antoon Lorentz was a Dutch physicist who shared the 1902 Nobel Prize in Physics with Pieter Zeeman for the discovery and theoretical explanation of the Zeeman effect. He also derived the transformation equations which formed the basis of the special relativity theory of Albert Einstein, according to the biography published by the Nobel Foundation. It may well be said that Lorentz was regarded by all theoretical physicists as the world's leading spirit, who completed what was left unfinished by his predecessors and prepared the ground for the fruitful reception of the new ideas based on the quantum theory. For this he received many honors and distinctions during his life, including, from 1925 to his death in 1928, the role of chairman of the exclusive International Committee on Intellectual Cooperation. Biography. Early life. Hendrik Lorentz was born in Arnhem, Gelderland, the son of Gerard Frederick Laurance, a well-off nurseryman, and Gertrude van Ginkel. In 1862, after his mother's death, his father married Luberta Hux. Despite being raised as a Protestant, he was a freethinker in religious matters. From 1866 to 1869 he attended the Hodgery Burger School in Arnhem, a new type of public high school recently established by Johann Rudolf Thorbecke. His results in school were exemplary. Not only did he excel in the physical sciences and math, but also in English, French, and German. In 1870 he passed the exams in classical languages which were then required for admission to university. Laurance studied physics and mathematics at the Leiden University, where he was strongly influenced by the teaching of astronomy professor Friedrich Kaiser. It was his influence that led him to become a physicist. After earning a bachelor's degree, he returned to Arnhem in 1871 to teach night school classes in mathematics, but he continued his studies in Leiden in addition to his teaching position. In 1875 Laurance earned a doctoral degree under Pieter Zeeman on a thesis entitled Over de theorie der terugkasting en brekking van het licht, in which he refined the electromagnetic theory of James Clerk Maxwell. Career. Professor in Leiden on 17 November 1877, only 24 years of age. Hendrik Antoon Lorentz was appointed to the newly established chair in theoretical physics at the University of Leiden. The position had initially been offered to Johann van der Waals, but he opted for a position at the Universiteit van Amsterdam at the last moment. On 25 January 1878 Laurance delivered his inaugural lecture on de moleculaire theorieën in de natuurkunde. In 1881 he became member of the Royal Netherlands Academy of Arts and Sciences. During the first 20 years in Leiden, Laurance was primarily interested in the theory of electromagnetism to explain the relationship of electricity, magnetism, and light. After that, he extended his research to a much wider area while still focusing on theoretical physics. Laurance made significant contributions to fields ranging from hydrodynamics to general relativity. His most important contributions were in the area of electromagnetism, the electron theory, and relativity. Laurance theorized that atoms might consist of charged particles and suggested that the oscillations of these charged particles were the source of light. When a colleague and former student of Laurance's, Pieter Zeeman, discovered the Zeeman effect in 1896, Laurance supplied its theoretical interpretation. The experimental and theoretical work was honored with the Nobel Prize in Physics in 1902. Laurance's name is now associated with the Lorentz-Lorenz formula, the Lorentz force, the Lorentzian distribution, and the Lorentz transformation. Electrodynamics and Relativity. In 1892 and 1895 Laurance worked on describing electromagnetic phenomena in reference frames that move relative to the luminiferous ether. He discovered that the transition from one to another reference frame could be simplified simplified by using a new time variable which he called local time. The local time depended on the universal time and the location under consideration. By that, he could explain the aberration of light and the result of the Fizeau experiment. Lorentz's publications made use of the term a local time without giving a detailed interpretation of its physical relevance. In 1900 and 1904, Henri Poincaré called local time Lorentz's most ingenious idea, and illustrated it by showing that clocks in moving frames are synchronized by exchanging light signals that are assumed to travel at the same speed against and with the motion of the frame. In 1892, with the attempt to explain the Michelson-Morley experiment, Laurance also proposed that moving bodies contract in the direction of motion. In 1899 and again in 1904, Laurance added time dilation to his transformations and published what Poincaré in 1905 named Laurance transformations. It was apparently unknown to Laurance that Joseph Larmor had used identical transformations to describe orbiting electrons in 1897. Larmor's and Lorenz's equations look somewhat dissimilar, but they are algebraically equivalent to those presented by Poincaré and Einstein in 1905. Lorenz's 1904 paper includes the covariant formulation of electrodynamics, in which electrodynamic phenomena in different reference frames are described by identical equations with well-defined transformation properties. The paper clearly recognizes the significance of this formulation, namely that the outcomes of electrodynamic experiments do not depend on the relative motion of the reference frame. The 1904 paper includes a detailed discussion of the increase of the inertial mass of rapidly moving objects in a useless attempt to make momentum look exactly like Newtonian momentum. It was also an attempt to explain the length contraction as the accumulation of stuff onto mass, making it slow and contract. Laurance and special relativity. In 1905, Einstein would use many of the concepts, mathematical tools and results Laurance discussed to write his paper entitled On the Electrodynamics of Moving Bodies, known today as the theory of special relativity, because Laurance laid the fundamentals for the work by Einstein. This theory was originally called the Lorentz-Einstein theory. In 1906, Laurance's electron theory received a full-fledged treatment in his lectures at Columbia University, published under the title The Theory of Electrons. The increase of mass was the first prediction of Laurance and Einstein to be tested, but some experiments by Kaufmann appear to show a slightly different mass increase. This led Laurance to the famous remark that he was about to on Latin. The confirmation of his prediction had to wait until 1908 and later. Laurance published a series of papers dealing with what he called Einstein's Principle of Relativity. For instance, in 1909, 1910, 1914. In his 1906 lectures published with additions in 1909 in the book The Theory of Electrons, he spoke affirmatively of Einstein's theory. It will be clear by what has been said that the impressions received by the two observers AO and A would be alike in all respects. It would be impossible to decide which of them moves or stands still with respect to the ether, and there would be no reason for preferring the times and lengths measured by the one to those determined by the other, nor for saying that either of them is in possession of the true times or the true lengths. This is a point which Einstein has laid particular stress on, in a theory in which he starts from what he calls the principle of relativity. I cannot speak here of the many highly interesting applications which Einstein has made of this principle. His results concerning electromagnetic and optical phenomena, agree in the main with those which we have obtained in the preceding pages, the chief difference being that Einstein simply postulates what we have deduced with some difficulty and not altogether satisfactorily, from the fundamental equations of the electromagnetic field. By doing so, he may certainly take credit for making us see in the negative result of experiments like those of Michelson, Rayleigh and Brace, not a fortuitous compensation of opposing effects, but the manifestation of a general and fundamental principle. It would be unjust not to add that, besides the fascinating boldness of its starting point, Einstein's theory has another marked advantage over mine, whereas I have not been able to obtain for the equations referred to moving axes exactly the same form as for those which apply to a stationary system. Einstein has accomplished this by means of a system of new variables slightly different from those which I have introduced, though Laurance still maintained that there is an ether in which resting clocks indicate the true time. 1909. Yet, I think, something may also be claimed in favor of the form in which I have presented the theory. I cannot but regard the ether, which can be the seat of an electromagnetic field with its energy and its vibrations, as endowed with a certain degree of substantiality, however different it may be from all ordinary matter. 1910. Provided that there is an ether, then under all systems X, Y, Z, T, 1 is preferred by the fact that the coordinate axes as well as the clocks are resting in the ether. If one connects with this the idea that space and time are completely different things, and that there is a true time, then it can be easily seen that this true time should be indicated by clocks at rest in the ether. However, if the relativity principle had general validity in nature, one wouldn't be in the position to determine whether the reference system just used is the preferred one. Then one comes to the same results as if one denied the existence of the ether and of true time, and to see all reference systems as equally valid. Which of these two ways of thinking one is following can surely be left to the individual. Laurance also gave credit to Poincaré's contributions to relativity. Indeed, for some of the physical quantities which enter the formulas, I did not indicate the transformation which suits best. That was done by Poincaré and then by Mr. Einstein and Minkowski. I did not succeed in obtaining the exact invariance of the equations. Poincaré, on the contrary, obtained a perfect invariance of the equations of electrodynamics, and he formulated the postulate of relativity, terms which he was the first to employ. Let us add that by correcting the imperfections of my work he never reproached me for them. Laurance and general relativity. Laurance was one of few scientists who supported Einstein's search for general relativity from the beginning. He wrote several research papers and discussed with Einstein personally and by letter. For instance, he attempted to combine Einstein's formalism with Hamilton's principle and to reformulate it in a coordinate-free way. Laurance wrote in 1919, "The total eclipse of the Sun of May 29 resulted in a striking confirmation of the new theory of the universal attractive power of gravitation developed by Albert Einstein, and thus reinforced the conviction that the defining of this theory is one of the most important steps ever taken in the domain of natural science." Laurance and quantum mechanics. Laurance gave a series of lectures in the fall of 1926 at Cornell University on the new quantum mechanics, in which he presented Erwin Schrödinger's wave mechanics. A typescript of the lecture notes is available. Assessments. Einstein wrote of Laurance, 1928, "The enormous significance of his work consisted therein, that it forms the basis for the theory of atoms and for the general and special theories of relativity." The special theory was a more detailed expose of those concepts which are found in Laurance's research of 1895. 1953. For me personally he meant more than all the others I have met on my life's journey. Poincaré said of Lorenz's theory of electrodynamics, "The most satisfactory theory is that of Lorentz. It is unquestionably the theory that best explains the known facts, the one that throws into relief the greatest number of known relations. It is due to Laurance that the results of Fizeau on the optics of moving bodies, the laws of normal and abnormal dispersion and of absorption are connected with each other. Look at the ease with which the new Zeeman phenomenon found its place, and even aided the classification of Faraday's magnetic rotation, which had defied all Maxwell's efforts." Paul Langevin said of Laurance, "It will be Lorenz's main claim to fame that he demonstrated that the fundamental equations of electromagnetism also allow of a group of transformations that enables them to resume the same form when a transition is made from one reference system to another. This group differs fundamentally from the above group as regards transformations of space and time." Laurance and Emile Wickert had an interesting correspondence on the topics of electromagnetism and the theory of relativity, and Laurance explained his ideas in letters to Wickert. The correspondence between Laurance and Wickert has been published by Wilfried Schroeder. Laurance was chairman of the first Solvay conference held in Brussels in the autumn of 1911. Shortly after the conference, Poincaré wrote an essay on quantum physics which gives an indication of Lorenz's status at the time. At every moment could be heard talking of the which they contrasted with the old mechanics. Now what was the old mechanics? Was it that of Newton, the one which still reigned uncontested at the close of the 19th century? No, it was the mechanics of Lorentz, the one dealing with the principle of relativity, the one which, hardly 5 years ago, seemed to be the height of boldness. Change of priorities. In 1910, Laurance decided to reorganize his life. His teaching and management duties at Leiden University were taking up too much of his time, leaving him little time for research. In 1912, he resigned from his chair of theoretical physics to become curator of the physics cabinet at Teles Museum in Haarlem. He remained connected to Leiden University as an external professor, and his Monday morning lectures on new developments in theoretical physics soon became legendary. Laurance initially asked Einstein to succeed him as professor of theoretical physics at Leiden. However, Einstein could not accept because he had just accepted a position at ETH Zurich. Einstein had no regrets in this matter, since the prospect of having to fill Laurence's shoes made him shiver. Instead, Laurance appointed Paul Ehrenfest as his successor in the chair of theoretical physics at the Leiden University, who would found the Institute for Theoretical Physics, which would become known as the Laurance Institute. Civil work. After World War I, Laurance was one of the driving forces behind the founding of the Wetenschappelijke Commissie van Advies en Onderzoek in het Belang van Volkswelvaart en Weerbaarheid, a committee which was to harness the scientific potential united in the Royal Netherlands Academy of Arts and Sciences for solving civil problems, such as food shortage which had resulted from the war. Laurance was appointed chair of the committee. However, despite the best efforts of many of the participants, the committee would harvest little success, the only exception being that it ultimately resulted in the founding of TNO, the Netherlands Organization for Applied Scientific Research. Laurance was also asked by the Dutch government to chair a committee to calculate some of the effects of the proposed Electrodynamics flood control dam on water levels in the Waddenzee. Hydraulic engineering was mainly an empirical science at the time, but the disturbance of the tidal flow caused by the Electrodynamics was so unprecedented that the empirical rules could not be trusted. Originally, Laurance was only supposed to have a coordinating role in the committee, but it quickly became apparent that Laurance was the only physicist to have any fundamental traction on the problem. In the period 1918 till 1920, 1926, Laurance invested a large portion of his time in the problem. Laurance proposed to start from the basic hydrodynamic equations of motion and solve the problem numerically. This was feasible for a human computer because of the quasi-one-dimensional nature of the water flow in the Waddenzee. The Electrodynamics was completed in 1932, and the predictions of Laurance and his committee turned out to be remarkably accurate. One of the two sets of locks in the Electrodynamics was named after him. In January 1928, Laurance became seriously ill, and died shortly after on February 4. The respect in which he was held in the Netherlands is apparent from Owen Willens Richardson's description of his funeral. The funeral took place at Haarlem at noon on Friday, February 10. At the stroke of 12, the state telegraph and telephone services of Holland were suspended for 3 minutes as a revered tribute to the greatest man the Netherlands has produced in our time. It was attended by many colleagues and distinguished physicists from foreign countries. The president, Sir Ernest Rutherford, represented the Royal Society and made an appreciative oration by the graveside. Unique 1928 film footage of the funeral procession with the lead carriage followed by 10 mourners, followed by a carriage with the coffin, followed in turn by at least 4 more carriages, passing by a crowd at the Grote Markt, Haarlem from the Zeilstraat to the Smederstraat, and then back again through the Grote Houtstraat towards the Bartelgerestraat. On the way to the Algemeen Begrafenis at the Cleveland has been digitized on YouTube. Einstein gave a eulogy at a memorial service at Leiden University. Legacy. Laurance is considered one of the prime representatives of the Second Dutch Golden Age, a period of several decades surrounding 1900 in which the natural sciences in the Netherlands flourished. Richardson describes Laurance as a man of remarkable intellectual powers. Although steeped in his own investigation of the moment, he always seemed to have in his immediate grasp its ramifications into every corner of the universe. The singular clearness of his writings provides a striking reflection of his wonderful powers in this respect. He possessed and successfully employed the mental vivacity which is necessary to follow the interplay of discussion, the insight which is required to extract those statements which illuminate the real difficulties, and the wisdom to lead the discussion among fruitful channels, and he did this so skillfully that the process was hardly perceptible. M.J. Klein wrote of Laurance's reputation in the 1920s. For many years physicists had always been eager to hear what Laurance will say about it when a new theory was advanced, and, even at 72, he did not disappoint them. In addition to the Nobel Prize, Laurance received a great many honors for his outstanding work. He was elected a foreign member of the Royal Society in 1905. The Society awarded him the Rumford Medal in 1908 and the Copley Medal in 1918.